Hello everybody, I am Ranjita from Center from Quantum Technology, National University, Singapore. Today I am going to talk about this optical frequency reference for nanosatellite technology missions, which is a bilateral project between the Humboldt University, Berlin and National University, Singapore, and CQT is representing the National University, Singapore. With this, I would like to thank the organizer of this IPS 2020 for giving us an opportunity to present our work here. So the presentation will start by motivating you why we were doing this kind of project related to science and technology in the nanosatellite missions. And then if since people might ask that there are existing project with the conventional satellite, what is the advantage? I'm trying to answer some of the questions and during these presentations. And then next we will discuss about our development in this ongoing project. So there are two main milestones which we wanted to finish for the advancement of this project is the revision spectroscopy setup and the control electronics. And then with this there will be the discussion of this future outlook, like in the near future what we plan to do using this kind of project developments and achievements. Okay, so main motivations in pursuing this kind of research is to explore the advantage of taking the quantum science and technology mission in space, and in diverse areas like in communications, navigations, sensing, and also in the many fundamental physics problems. And as we all know that there are some large-scale quantum testbed in space, like using the conventional satellite. Even though they are promising research programs, they take a huge cost of money while developing this kind of project. So in order to maximize the efficiencies, we try it increase the maximize the efficiencies, it increase the complexity of the system developments, so which in turn increase the lead time of the project delivery. So this in fact pose a high barrier to the number of scientific communities which were trying to pursue this kind of research. And so in order to fill this gap, we think that nanosatellite technology mission based on the CubeSat will fill the gap, which will accelerate our experiments and studies of this quantum science and technologies in the space by doing many rounds of iterations and developments, since it requires only a modest budget to develop this kind of project and launching, so which in fact increase the number of launching and try to optimize our efficiencies and developing this kind of project deliveries by studying the small components launching into the space. And so this will be possible by developing miniaturization technology, which I will be discussing in the coming slides. So in the right side picture shows the unit of the CubeSat, and there is one unit of CubeSat and two units of CubeSat stacked together. Each unit can be act as an independent nanosatellite. So in this slide, what I wanted to do is that I want to convince that the CubeSat is a good choice of doing the quantum science and the technology mission in space, because of the continuous effort of the miniaturizations and the development of the ruggedized system. It is possible now, and in order to prove that this technology is compatible with nanoscience and technology in space studies. So the important parameter to evaluate is the technological readiness level of the system in terms of the science package and the communications package. So this can be proved with given some examples like the Spooky satellite, which carries QKD source with polarization entangled sources in 2019. From NUS, and also there is another project to study the quantum gravity sensing from UK called CASPA. And if you wanted to know more details about this, you can go to these links which I have given below, and you can write to me for more information. And then if you ask me, okay, so people have done this, they have studied and proved some of the proof of principles ideas, but what is your status of the project? The present status of a project is of technology readiness level 4, which means we are testing and assembling most of the system and testing the subsystem vigorously in our laboratory. So I discussed earlier for this development of this project, in this project we have two biggest milestones. One is the optical system, another one is the electronic system. In the optical system is mainly the building the modules of the laser spectroscopy system, which will be compact, robust, and a standalone system for doing this frequency reference. So our system will be based on the Doppler free saturation spectroscopy of the rubidium atoms, and we are going to log the frequency of the laser using frequency modulations, and our target stability is of the order of 10⁻⁻14 per day. The right side image shows the CAD image of the spectroscopy standalone system we are developing, and it's based on the monolithic and distributed feedback lasers. So all the size, the whole box size will be coming around a 38 centimeter cube box. So you can see the actual system which is assembling in FPH Berlin. So parallel to that, the another bigger milestone is also developing the control electronic system. So we have to develop all the control electronic system which will be linkable with satellite and remotely control system. So to give you an example of the laser current driver which we're developing, the right side picture shows the image of the current driver, which is in a box of 8 centimeter into 9 centimeter dimension, and which this controller should be able to do all the frequency switching and the locking of the lasers. And apart from this, we have to develop the digital control unit as which will be linkable with the space platform for data transfer and sending our instructions for controlling the systems. And this whole system will be assembled, like as I discussed, 18 to 90, and the box will be a 30mm height box. So if these two milestone is developed, and then the next step is to do the quantization, rigorous quantizations and the calibrations of the system. So for the laser current driver which we are developing in NUS, we are doing some of the characterizations. So here I just wanted to show that the first generations results which we have do the analysis some few months back, and then the second generation is already delivered to us after manufacture. So we have done some improvement and added some other parts which were not there in the previous system. So first of all, we do the response measurements of the circuit and see that its response is of the order of 230 milliseconds, and the system is controlled by an SPI controlled 16-bit DAC for remote control. And also we measure that the repeatability of the set point and the noise of the system, and we found that the repeatability of our current controller is within plus minus 6 microampere, which is quite good. And most of the noise components in the system is in the linear to represent, which we kind of expected. And in order to give a bound in the frequency noise in the current circuit, we do power spectral density analysis of the laser current. So from there we kind of evaluated that the RMS noise in the circuit is 300 nanoampere, which is slightly higher than what we are expected, and we attribute this noise is coming from our first generation's design error in some of this track. So we actually did cut and resolder some of this track to make it working. So I think that could be the reason why its noise is slightly higher. In the next generations, like which I am going to characterize now, it should be better and improve. So the current limit is 160 milliampere for the system. I think this is quite good and reasonable laser current driver. So in the validation process, as I discussed earlier, for the laser performance, we have to do long and the short-term length deviation. It's the same for the optical system, which are developed in the Berlin also. And then qualify all the thermal and the mechanical effect, including the shocks, and which in order to find the compatibility in launching in the satellite project. For this, we have to do many ground-based developments, qualifications by simulating the environment and the effect which we are going to face in the space in terms of shocks, temperature variations, and the changes of the cosmic radiations and etc. So here in this slide, what I wanted to tell you is that using our developed laser control system and optical system, in our immediate future, we plan to demonstrate the magneto-optic system using our developed techniques. So we have the ideas how it's going to be done, and we have developed some of the system in the lab, like pulse switchable single laser system for cooling and the repumping of the rubidiums, and miniaturized UHV components, and control electronics with space linkable platform. So with the few improvement and the development of some of these other equipments, we should able to demonstrate the performance of our system in this cold atom system. So with this, I would like to summarize whatever I have discussed with you and presented to you today. The first part of my talk, I tell you that this CubeSat is a good choice of doing the quantum science and technology missions in space, which will help us to enhance or improve the conventional big satellite project, which require a huge sum of money in performing, and then more and more scientific communities will able to assess this kind of technology for doing their studies. And in between there, I have discussed also the progress and developments toward realizing what we have claimed that in using the CubeSat optical frequency reference. So there is this optical frequency part which we're developing in the FPH Berlin, and also this optical frequency reference will be based on the rubidium absorption spectroscopy with a target stability of 10⁻⁻14 per day. And in the later part, I also discussed that we have developed another milestone, the miniaturized electronic control system, which is remotely control, which can be spatially linkable, and then to transfer our data and also to transfer our instructions for the proper functioning of the system. And also we have developed a laser current driver, which is a dimension of 8 centimeter into 9 centimeter, to give an example, and its characterization. Some of the characterization of the first generation is also discussed. And then okay, here I came to the end of my presentation. So I would like to thank all my co-workers, including Marcus and Alex, which is the supervisor of this project. If somebody wants to know more details or any clarification it is needed, please feel free to write to me at this following email address. So thank you all.